Question 13 begins with a definition. Explain what's meant. So no point me spending my time telling you that. It's in your books. Look it up. Part B is asking you to find the gravitational potential at the surface of the moon. But importantly, it says use the following data. And the only data it tells you is it tells you the gravitational potential at the surface of the Earth. It tells you that the mass of the Earth is 81 times the mass of the moon, and the radius of the Earth is 3.7 times the radius of the moon. Now some of you just happen to know what the mass of the Earth is and what the radius of the Earth is. But you're not supposed to use that, because the question says just use this information here. So let's think what we know about gravitational potential. The data sheet gives us this formula for a radial field. Potential is minus gm over r. Now we're trying to find the potential for the surface of the moon, and we're told the potential for the surface of the Earth. So we've got two different potentials to deal with, because we've got two objects with different masses and different radiuses. So we can't have one equation where you've got a symbol meaning two different things. So what I would do is I would write the equation twice. The potential for the surface of the Earth will be minus g times the mass of the Earth divided by the radius of the Earth, and that for the moon, potential for the moon must be minus g times the mass of the moon divided by the radius of the moon. So this is what I'm trying to find. Now, what do I know about it? Well, all I know about the mass of the moon, I know that the mass of the Earth is 81 times the mass of the moon. In other words, the mass of the moon is the mass of the Earth divided by 81. So instead of writing the mass of the moon, I'm going to write the mass of the Earth times 1 over 81. And instead of writing the radius of the moon, what do I know about the radius of the moon? I know that the radius of the moon, the radius of the Earth is 3.7 times the radius of the moon. So the radius of the moon must be 1 divided by 3.7 times the radius of the Earth. So what I've got here is I've got minus g times the mass of the Earth divided by the radius of the Earth times 1 over 81 divided by 1 over 3.7, which is minus g times the mass of the Earth over the radius of the Earth times 1 over 81 divided by 1 over 3.7, it's the same as times 3.7 divided by 81, and minus g times the mass of the Earth divided by the radius of the Earth. That's the gravitational potential on the surface of the Earth, and that number's given. So if I put in the value that's given for the potential at the surface of the Earth, multiply it by 3.7 divided by 81, that gives me the potential at the surface of the moon. And all I've used is the data that was in the question, like it told me to. The last part was to complete the graph. Most people got the right general shape, but probably didn't go into enough detail. Very important. We only draw the parts that are outside the Earth and outside the moon. So we make sure that our graph doesn't come any further to the left than the surface of the Earth. So we'd start there at the surface of the Earth. Similarly, we know that we don't go inside the moon, so we're going to finish here at the surface of the moon. We know the starting value for this. You'll have worked out the value at the surface of the moon, which is quite a lot smaller than the potential at the Earth. So although you don't need to draw it exactly to scale, you can roughly scale what the potential at the surface of the moon is from the answer you've got. Certainly not going to be anywhere down here, it's going to be somewhere right up here. Got those points. We get the general shape. Now if you want to put some care into it, we know that the field, so we know that the potential changes 1 over r. So if we doubled our distance from the centre of the Earth by coming out to here, we know we're going to have halved the potential. And if we double that distance again, we'll have halved the potential again. So that can help you to get a slightly more accurate curve. But what matters is that your curve comes up almost to zero, not quite to zero, and then it falls back down to the surface of the moon. And this peak is much nearer the moon than it is to the Earth.